In this video, we're going to complete the examples for manganese and aluminum. We're going to make some electron configurations for these elements, and then we're also going to draw an energy level diagram. So we're going to start off with the electron configuration for manganese. I want to do that first using our periodic table technique. So let's go ahead and just make a bit of space here and go ahead to use our periodic table to figure out the electron configuration for manganese. And then we'll do the same thing for aluminum when we're done with manganese. All right. So let's find where manganese is in our periodic table. Manganese is over here. And so when we're doing the electron configuration for manganese, we're going to start off with hydrogen as 1s1, 1s2. So 1s2 is done. Then we have 2s2. So 2s1, 2s2. Then 2p1 all the way to 2p6. So I'm going to write that out. 1s1, 2s2, 2p6. Then after we are done with 2p6, we're going to go to 3s1, 3s2, and then 3p1 to 3p6. So 3s2, 3p6, and back to finish up here. So now we need to do 4s1, 4s2, and now we're going to 3ds, 3d1, 2, 3, 4, 5. So 4s2 and 3d5. That's our complete electron configuration for manganese. Now we want to make the shorthand. So for manganese, the previous noble gas is, so here's manganese. The noble gas just before it is argon. And so that's the one that ends in 3p6. It's in period 3 here. 3p6 would be the last part to that configuration for argon. So it's really all of this here, 1s2 all the way to 3p6, which is the highest filled p orbital, p subshell we have. So I'm going to replace all that by argon and then have 4s2, 3d5. And that would be the shorthand notation for manganese. Now we're going to try to make the energy level diagram for it, and we're just going to fill up the correct number of electrons for manganese using our electron configuration. They should match. So manganese has how many electrons? It has 25 electrons. So there's 25 electrons for manganese. Starting here, 1, 2, 3, 4. Then one at a time, 5, 6, 7, 8, 9, 10. Then 11, 12. Then 13, 14, 15, 16, 17, 18. Then 19, 20, 21, 22, 23, 24, 25. And there we have it, the energy level diagram for manganese, which should match the electron configuration for manganese as well. You'll have 25 electrons in the electron configuration, 25 in the energy level diagram. And so let's just show you how this all connects to quantum numbers once again. Let's circle an electron. Here we go, right here. We'll circle this electron in manganese. If I want to give the quantum numbers for this electron, it is in the third energy level, 3. So n is equal to 3. It is in D, a D sublevel. So the L is going to be not 0, not 1, but 2. In terms of ML, remember we can have -2, -1, 0, +1, and then +2. So that's -2, -1, 0, +1, and +2. So we are in +2 ml. And then lastly, for ms, the way we have it drawn here is that this is pointing up. So this is our +½ ms. And so for each electron in this energy level diagram, you can provide its unique set of quantum numbers. Let's go ahead and try this example for aluminum now for the electron configuration, and then the shorthand, and then afterwards the energy level diagram. So you should always pause the video and try it yourself first, and then check the work. So we are doing this for aluminum. So we're going to just erase some of the markings here so we can be nice and neat and clear. Aluminum is not a very difficult one to do. It's pretty straightforward. It's not going to be a very long one, like let's say bromine, for example. Aluminum is right here. So we have 1s1, 1s2, 2s2, and then 2p1 all the way to 2p6. And then 3s1, 3s2, and then over here, 3p1. So we had 1s1 or 1s2, 2s2, 2p6, 3s2, and then 3p1. And that's because aluminum falls right over here. And so we get our 1s2 filled up, our 2s2 filled up, our 2p6 filled up, our 3s2 filled up, and then our 3p1 right here. And that would be the electron configuration for aluminum. Now, the shorthand notation, we want to find the highest p level that's all filled up, and that would be up to 2p6. And we replace that by the noble gas that comes before aluminum, which would be right here. And in our periodic table, that's neon. So this is neon. And then we have 3s2, 3p1. Neon, 3s2, 3p1. Now we can go ahead and make our electron configuration or our energy level diagram for aluminum. So let's just go take a look. Aluminum has 13 electrons. So there are 13 electrons a place. 1, 2, 3, 4, singly first, 5, 6, 7, 8, 9, 10, 11, 12, and 13. And so now we have our energy level diagram for aluminum, which should match the electron configuration for aluminum by having the same number of electrons. And one more example we'll do with quantum numbers. Suppose I wanted you to find the quantum numbers for the valence electrons of aluminum. Now, the valence electrons generally, unless you're in the transition metals, generally the valence electrons for something that's in your p blocks, they're going to be your basically your highest S and P values. So your valence electron for anything, let's go to our periodic table here. For most things in this region here, they're going to be the S and P. For most things in here, they're going to be simply your highest S value. And this over here is going to be your highest S as well, just because it's it only has S electrons. Now, it's a bit weird for transition elements. Typically, you can access the D electrons plus the highest S value as well. So D plus your highest S value. There are some exceptions, but that's usually the approach. And then for elements in here, in the lantanides and actinides, their valence electrons, they vary quite a bit, but generally it's your F, D, and then your highest S level as well. So those are your general valence electrons for things that fall here. Now, we're not going to ask you a lot of questions with those complex ones, but for something like aluminum, I could say, what are the quantum numbers for the valence electrons of aluminum? And so the valence electrons of aluminum are these ones over here, the S and the P, because as I said, things that fall generally in this area here, their valence electrons are the highest S and P levels. And so for aluminum, we can write out the quantum numbers for the S and the P electrons. So this is just an extra problem. It wasn't part of this worksheet, but I'm deciding to add that in there. We have our 3s2. And so for our 3s2 electrons, they basically look like this here. So we have n is equal to 3. And then for our L value, well, it's 0 because they're an S. For ML, well, there's only one orientation, so it's 0. And then for MS, since there's 2 in there, well, they could be plus or minus 1/2. And then for your 3p electron, this one here, well, it's n is equal to 3. L is equal to 1 this time. The ML, you have choice. I mean, theoretically, it could be in any one. If I didn't have a drawing, it could be, um, so you have -1, 0, +1. So it could theoretically be any one of these, but based on our drawing, it's -1 is the first one. And then our MS, based on our drawing, is the +1/2. And so again, if I asked you for quantum numbers for the valence electrons, you find what your valence electrons are. So it's the highest energy level S and P for elements that are in these P blocks. If they were in the S blocks, it's just the highest level S. If they were in the D block, it's generally the highest level S and then also the D, because that's why some of the elements have more than one possible charge, because they can access their D electrons to make ions, and they're still stable. And then if you were in the F block, it's these ones here that are your valence electrons, the F, D, and S. But typically you won't see us asking you too many questions about the F level electrons. So at this point, we've seen how to do electron configurations, shorthand complete, and also the energy level diagrams for neutral atoms, so things that are not charged, things that are not ions. We saw how to connect them to the quantum numbers, and we briefly saw the idea of valence electrons in our electron configurations. In the next videos, you'll see how to write electron configurations for ions, and then you'll also learn about some anomalies, some electron configuration exceptions, or things that, let's just say, break the rules.